The original title of this talk was "You're in a Maze of Twisty Little Traces All Alike." And I intended to draw a parallel between software development and an old school adventure game, in that you're not really sure of where you are, neither are you sure of where you are going. But the organizer changed the title, so that's not perhaps that clear anymore, but we'll go with this title for today. But before I start, those of you who doesn't know me, I'm a researcher at the Swedish Institute of Computer Science, where I usually work with programming tools, programming languages, and distributed systems. But enough about me. This talk is a brief introduction to the Beam, a just-in-time compiler, which I've been developing for this past year and a half, I think. And then I talked about it last year, so this is more or less an update of what I've been doing since then. This talk is structured as follows. I start with a short introduction to just-in-time compilation, the Beam virtual machine. Erik Stenman gave a good overview already, so I can probably shorten that part. I'll tell you about my goals with this Jit compiler before I describe the tools that I've been using. And when that is done, I'll go into details about how jitting can be done for Beam. And then I'll walk through the evolution of the Beam JIT before I wrap up with some future work and questions at the end. Just-in-time compilation is an optimization technique that is used to improve the performance of Vim-based languages. It's nothing used. It's been fairly commonly used. It exists, Jit compiler, for many cool languages such as Python, Smalltalk, Java, JavaScript. So it's about time that Erlang gets one. I've previously mentioned Beam, and Erik talked about it before the break. Beam is the name of the Erlang virtual machine. It's a register machine. It has approximately 150 instructions, which during loading are transformed with a peephole optimizer to around 450 macro instructions. And the Beam is written in C. It's mostly handwritten C. Some of it is generated. And unfortunately, there is no authoritative description of the semantics of these instructions. We have only the C code. But when I was asked to build this Jit compiler, I set up a number of goals for it. The goals are that I want to do as little manual work as possible, because I'm a computer scientist and manual work is boring. You want to automate it. I wanted to preserve the semantics of plain Beam. So I didn't want a user to see any difference between running the jitting version than compared to the traditional version. I also wanted the JIT to stay in sync with the traditional implementation. So if the OTP people find a bug or add an instruction, that should automatically be possible to JIT it. I shouldn't have to keep up with them. And I also want a native code generator that is state of the art. And the key thing to try to pull this off was that I wanted to parse and extract the semantics of the Beam operations from the C code that implements them. That way I could skirt around this problem of not having a specification. And then use the information I extracted from the implementation to produce the input I need for my JIT. But before I go into how this can be achieved, I would like to motivate why, because we have at least Eric and is Kostis here? No, he's not here, but there you are. We have the HiPE people here. So why would you want a JIT when you have HiPE? Well, there are a number of reasons. A JIT will automatically give us cross-module optimization. We have a potential of saving memory, as native code tends to be much larger than the corresponding Beam code. Also, if you're doing tracing as part of debugging, you will, if you're using HiPE, have to switch to completely interpreting your code, or at least modules. And if you're having a JIT, you could instead just let the JIT the tracing version of your code. And also, a big thing is that modules stay independent from the target architecture. So there is no need for cross-compilation, and there is no need to actually couple the released binaries, the released modules, to a particular version of, or particular build of your emulator. With that out of the way, I tell you about the tools that I'm using to actually pull this off. The main tool I use is LLVM. LLVM is a compiler infrastructure which contains a collection of modular and reusable compiler and toolchain technologies. It uses a low-level assembly-like language called LLVM-IR. It has backends for a lot of CPUs, a lot of optimizations. And as a complement to LLVM, there is a front end called Clang, which parses C-type languages, so C, C++, Objective-C, so on. And it in turn behaves more or less as GCC, but as output it produces LLVM-IR. And that compiler is also packaged in the form of a library. So using the library, which is called libclang, you can parse a C module and get hold of the abstract syntax tree, which is exactly what you want if you want to extract the semantics of code implementing the Beam instructions. So that was the background. Let's get back to the problem, the JIT. Well, the initial approach we've chosen is that we want to make a tracing JIT. And a tracing JIT works by first having a profiling stage where we find out which parts of the code that are frequently executed. And when those parts have been identified, we start tracing the code. And we trace the execution flow until we get back to the place we started the trace from, because then we have found a loop. And we assume that loops are probably where we spend most of our time. And when we have this trace and we have found a loop, we generate native code, and then we run it instead of running it inside the interpreter. And compared to some other tracing JITs, we have decided to do this on the level of the emulator. So we are not following single instructions. We are following parts of the instructions. So we're doing some kind of CISC to RISC translation on the fly when we do this. So in order to do this, what do we need to have support for in our virtual machine? Well, we need 3 basic execution modes. One is profiling, figuring out what's hot. The next one is tracing, figuring out which exactly is this hot code path we're following. And then we have to be able to run things in native code. And to do that, we have to support an efficient way of switching modes. That means turning from the profiling mode into tracing mode and back again, and then also passing state from the interpreting world to the native world where we're running native code. And then also we have a big part which is native code generation. We have to actually, from our trace, produce native code. And for that, we need the semantics for each instruction. And I've previously hinted about that. We use libclang to parse and interpret the Erlang Beam implementation. And we do some transformation on the code of the main interpreter loop. We flatten out all variable scopes. We remove loops and replace them with explicit gotos and ifs. We make all fall-throughs explicit. And more or less we turn our nicely, or at least roughly nicely structured C code into a spaghetti of a lot of gotos and single basic blocks. So what we're more or less creating is the control flow graph. And then when we have the control flow graph, we do liveness analysis on all the variables in it. And the illustration here is a part of the control flow graph of the Erlang interpreter. It's probably a tenth of it. I couldn't fit anything more on the slide. With that, it's time to look how the prototype has evolved during the last year. We have passed through at least 4 different distinct versions of the JIT system. Mark 1 was the one I talked about here last year. And now I'm up to Mark 4, which is the one I'm using right now. Mark 1 had everything needed to implement rudimentary JIT. It had support for profiling, meaning that, and that was implemented by a simple counter. So we had the compiler insert profile instruction at places in the code which could be the head of a loop. And then when we passed through these instructions, we just had a counter and we incremented each time we passed by it. And when the count was high enough, we said that, hey, it's time to start tracing. And that has the drawback that eventually we'll compile everything. But for toy examples, hello world loops and things like that, it serves its purpose. And the only thing you actually have to add to your implementation here is the implementation of that profiling instruction. I said that when we found something that was frequently executed, we turned on tracing. And to do that, we actually had to we have to record all the basic blocks we pass through. And we do that by switching to a new version of the interpreter, which we generate from our CFG. So that works so in the way that for each basic block we passed through, we record the identity of the basic block and the program counter value at that point in a log. And if that log becomes too long, we abort the trace and give up. But if we are lucky and get back to the profile instruction we started the trace from, we have found a loop. And then it's time to generate native code. But this switching between emulators from the non-tracing to the tracing version, then we use a trick. So Eric, before the break, talked about that, said that Erlang uses something called direct threading to optimize instruction dispatching. So here on the left, you see you have a direct threading example where the program counter points into code memory, and each opcode is represented by the address of the code that actually implements that particular instruction. But if we want to be able to switch between the modes, we have to add some indirection, and that's what we do here. We convert the Erlang beam to use something called indirect threading instead. So now what the program counter points out is actually just indexes, and those indexes are indexes into a table, and that table in turn contains the address of the implementation of the opcode. So if we want to switch from one implementation of the opcode to another, we just have to switch these tables. Unfortunately, that cost us some performance. So this graph here shows a benchmarking suite. It's the benchmarking suite Kostis and his team uses when they want to show off Beam. So, but here in this case, the height of the bars are normalized runtime. So I normalize the runtime of each of these benchmarks tests in a way so I can compare them to the unmodified system. And it's done in such a way so that if my modified system takes twice as long to run as the unmodified system, you get a runtime value of 1. If it's just as fast, takes the same time, you get a runtime value of 0. If my modified system is, say, twice as fast, it runs in half the time, then I get a benchmark value of minus 0.5. So positive is bad, negative is good. So you can see here at almost all cases except 2, it costs me performance to do this switch to indirect threading. So that's something we'll have to live with further on and have to try to make up in some way when we run native code. And the error bars you see are one standard deviation, so you can see how noisy these values are. And if you can see the legend up to the right, I plot them so to the left in the blue bar, all of them are 0 because that's what I normalize it against. But you can at least see how the unmodified system, how noisy it is, because you can see the error bar. So that's the cost for indirect threading. Now to native code generation. We generate our native code by just gluing together IR fragments that correspond to the basic blocks we have traced. And when we do that, we have to insert guards to make sure that we actually follow this trace that we have traced. Because if we execute code that will lead to another, a different execution trace, we have to detect that. And when we have done this, we hand off our IR trace to LLVM for optimization and native code generation. And these fragments of IR we glue together. Those we extract from our CFG. And we do it by chopping up the CFG, each basic block, into a C function, which we compile and then load at runtime. So we have templates which we can quickly glue together. So the figure illustrates that process where everything that's blue is done ahead of time when we build the system, and what is it? It's pink. The pink part to the right is done at runtime. Now I only have one of these mode switches left to describe, namely, how do we call native code? in the Mark I version of the JIT? Well, when we switch from interpreting mode to native mode, we pack up all the variables that are live into a structure and head it over to the native code, which in turn unpacks it and plugs in the value in its temporaries. And we do more or less the same when we switch back. And when we switch back, we jump into the emulator at the particular basic block where we should continue. This works. It actually works. It's correct. But the performance is pretty bad. And the reason for that, and I should say that pretty bad means six to 7 times slower. And the main reason for that is that if we have a piece of code looking like this in our emulator, in the unmodified system, the compiler would generate assembler code corresponding to this CFG. You see it in some way allocates a register for X, sets it in some way, it branches on it, and then in one branch it increments it, and the other one it decrements it. But now, when we support that we actually can restart instructions halfway through an instruction, then it's forced to do something like the part here on the right, where after each time it sets a register or a variable, it has to actually store it back into memory. So in this way, even if you're executing this fast path inside the interpreter, you have to pay for the cost for loading each value before you use it and storing it back into memory when you're done. Bad as this Mark I version was, with some minor tweaks, it was actually the first version that could compile OTP and pass the test suite without crashing. And in order to actually pass the test suite in a reasonable amount of time, I had to do some small tweaks. One of them was to make the profile time aware. So instead of just measuring execution count, I start measuring execution frequency. And also, I introduced blacklisting. So places or locations in the code where I almost all the time started tracing or produced code that almost failed, then I blacklisted those to not just repeatedly spend time trying to trace something that didn't pay off. Also, I added some things like garbage collection of traces so you could actually purge code and load new code, things like that. It didn't impact performance in any way, but it was time to do something to cut down on this overhead for loading and storing at least. So to do that, I figured that the unmodified system is pretty efficient. Björn did good work optimizing it. So I tried to modify it and change it as little as possible. And then instead have a completely separate trace interpreter, which I used for tracing. And then also, as there is a big problem of jumping back halfway through and the implementation of an instruction, I said that, hey, we can only enter the interpreter at the instruction boundaries. So then I needed a further version of the interpreter, which I used to just execute until the next instruction boundary. And to do this, we used some implementation tricks. I used liveness information from the control flow graph, and happily, it turns out that if you're looking at the set of variables that are live on entry to each at instruction boundaries, there are only 8 distinct sets. So it's actually possible to efficiently choose which set of live variables to restore, and also when we're calling native code, package that native code as just an ordinary function with a set of arguments. And the arguments are the live variables, which are live on entry to the trace. So you can just call it using an ordinary function pointer. Also, during cleanup, this cleanup interpreter which we use to execute until the next instruction boundary, they can be easily formulated as just functions which take the live variables as arguments, and then tailor recursively calls the next basic block in sequence, and then at the end still packs up the live variables and passes it back to the interpreter. This helps performance. Remember, I said that last time it took 6 to 7 times. It was 6 to 7 times slower. Now, if we look at the graph again, you see the worst case is 0.75 or so. So instead of 6 to 7 times slower, we're just twice as slow. So at least that was an improvement. Also, it turns out that changing things in the basic interpreter loop have big impacts on performance. So probably there is a large potential of optimizing this further by placing code in the right places and in the right sequence. Also, while running Mark II, I noticed a property that I attempted to fix in Mark III. It appears that we quite often compile a trace which is not representative, meaning that when we try to run it natively, we almost always fall off that trace during the first iteration. And to try to avoid that, I added a new mechanism which I call trace along. That means that the first time I found a loop, I don't compile it directly. Instead, I have it let it hang around for a while, and the next time I come here, I trace it again, and then I trace it and see that I actually follow the previous trace. And if I manage to do this multiple times, then I can be pretty sure that what I have is a representative trace. And then I go on to compiling. Unfortunately, that in turn leads to, instead of blacklisting things after we have traced and compiled them, we now blacklist things already while tracing. So we find a lot of places where we never find a representative trace. And the solution to that is more or less to allow more than one path inside the trace. And then instead of just generating native code when we were traced a certain number of times, we instead let the trace grow, and when we've traced from the same place multiple times without the trace growing, then we know that, well, now we probably have seen everything we will see, so now it's time to compile it. Unfortunately, then we get another performance hit, namely that it appears that a lot of LLVM's optimization and also native code generation is pretty sensitive to the number of basic blocks we give it, to the size of the control flow graph. So to try to solve that, I introduced something I call trace compression. So if these problematic traces, if you look at them, you find that there are things that look like loops inside them, or branches which separates the trace in two paths, which which share the same prefix, does something else, and then have the same tail parts, like the one here on the left. So the boxes are basic blocks. So you can see there, this one has the same basic block at top. Here are two different basic blocks, but then here, the lower part, the tails, they are the same sequence of basic block at the same instruction counter values. So the solution is then to try to compress this trace into something looking like the one on the right. So you actually make an explicit branch to the two parts and then merge it back together, and then so that way we can at least reduce the number of basic blocks we hand off to LLVM. Still, the compilation overhead pretty much dwarfs everything else. So also I should say that I'm running LLVM on an optimization level that corresponds to -02 if you're running GCC. You can see here, there are a bit of noise down here. The green bars are the normalized runtime for running the JIT with the JIT active from previously cold code. And you can see there is one here, something like 470 times. That's not very good. But if we zoom in, not everything is lost. We are actually faster than the unmodified system in some places. And I should probably tell you what these different bars mean. So you have the red bars, that is the system running interpreting. The JIT is completely disabled. The green one is running with the JIT enabled, and the gray ones are just running the benchmark when everything that is going to be JIT compiled has been JIT compiled. So you can see that there are some cases here at least where even running with the JIT enabled, we're actually faster than the unmodified system. That's good. If you instead look at the performance of the performance of the generated native code, like in this code, this slide, you see that it actually looks pretty good, at least on that part. So there are some cases where we have problems. This large group here on the left, where we make repeated calls, just function calls, if we study that, we see that these guards we insert in the native code, they are pretty costly, and that's where most of our performance goes here. And also these two peaks over here, where we have, these are the ring benchmarks, where the code we're tracing or the code we're executing behaves in the way that it's scheduled out, it gets a message, gets scheduled in, does something, and then it's scheduled out again. In some way it's a loop, but it passes through the scheduler. And as we've previously only been interested in loops, we have said that everything that passes through the scheduler, we can't trace it. These problems quite nicely show what we have to do next, where my next year's work is located. Well, the first one, I see that we should not fixate on finding loops. We must be able to handle these things that are typically message handlers, we're scheduled out, something happens, we get the message, and then we have to do something fast, and then send out a response, and then get scheduled out again. Also, in order to limit the cost of the guards, we have to implement some kind of Erlang aware constant propagation, so we should be able to eliminate many of them, because many of these checks check that this thing we're calling now, that function, that is actually that function, and we do that by checking the value in memory where the instruction pointer points to, and that is something that's actually a compile times constant in our case, although it's located in RAM, because it's code, and code is read-only, mostly. Also, we'll eliminate much of the overhead we have when we unpack intermediates inside code. That should also be able to improve our situation. The next big thing we have to do is to increase performance in plain interpreting mode. You saw that we had an overhead to almost twice as low. That's not good. And you saw we had this enormous overhead for compilation. And a way of masking that, at least, is to move compilation to a separate thread. We can't have a soft real-time system which goes off to lunch because it's compiling native code. Also, but that's a long-time goal, is to actually extend this tracing mechanism to extend outside the main interpreter loop, which we have limited ourselves to right now, because then we could perhaps do optimizations inside ETS or other frequently called things. Well, before we go to questions, I'd like to thank Ericsson for paying me to do these fun things, and also particular Kenneth Lundin. Is he here? No? Then his colleagues can tell him that I really appreciate that he understands the process of research and is not pushing for immediate and fantastic results, and that he lets these things take time. Well, thank you. Questions?
So, what do you do with hot code loading?
Hot code loading, well, you load the code and run. It's nothing special. Unless you mean purge, because then you actually have to track the traces. For a trace, you have to track the modules it touches. So if you purge a module, you remove those traces that involves that module. So then you'll take a hit in performance until you have profiled and jitted these parts again.
Have you compared those benchmarks to HiPE?
Yeah, but I haven't showed them because these benchmarks are clearly chosen to show up HiPE, so I'm not in their league yet. But hopefully one day I'll beat them.
Seems that there's no more questions. So thank you, Frej.